Okay, let's start. Good afternoon. So this week I want to start and finish the proof of the Moran-Hutchinson formula, which gives you the dimension, Hausdorff or Minkowski, dimension of certain fractals that are attractors of nice iterated function systems. But before that, obviously, we need to define the Hausdorff dimension. We need to finish the definition of it. Okay. So recall that we discussed this last time. So we talked about all this business about measure theory. And we had just defined this notion of the Hausdorff outer measure. And so here's a recalling of this. So I take a metric space and a parameter s. Recall that this Hausdorff outer measures were a family of outer measures on X. So the s is the parameter that parameterizes the outer measures. I take a subset A and an epsilon. I'm going to take epsilon to 0. So h to the s sub epsilon of A, which I think Barnsley denotes by m of A comma epsilon comma p or something. So for Barnsley, p is s. So it's basically this. I take a sequence of subsets, arbitrary subsets of X, such that each of these sets have diameter at most epsilon, and their union covers A. Okay? For any such sequence, I look at this infinite sum. I should also mention that even though I write it like this, I also allow finite collections. The point is that I have at most countably many elements, so that this sum can be made sense rather reasonably. And I take the sum of the diameters to the power s. And of course, I optimize. I take the least number I can get this way. And so in general, this is going to be a number between 0 and infinity, and infinity included. Okay, so I want to take epsilon to 0. Note that if I have this, then any C bullet whose diameters are bounded by epsilon 1 will also have diameters bounded by epsilon 2. In other words, possibly by decreasing epsilon, right, I'm going to have a larger infimum. So, is this correct? Yes. So if this is smaller, this should be larger. Okay. I think this is correct. If not,
epsilons are smaller than 1. Is that the idea?
That is not necessary for this. I mean, ultimately, yes, but I think for any two epsilons, if epsilon 1 is less than epsilon 2, and how do you argue for this? You say, now I'm questioning myself. Okay, let's see. Let me denote by curly C sub epsilon the collection of all such C bullets. And this is saying that C sub epsilon 1 is included in C sub epsilon 2. I am confused. Does any of you agree or disagree with this? What should be? Is it this way or the other way around?
I mean, somewhat intuitively in my mind, it's like if we have the epsilon larger, there's going to be less diameters we're adding because we're more easily covering that. But I think that sort of depends on how many diameters you have adding compared to the actual rate or diameter of those balls. But that was my intuition.
So do you agree or disagree with this?
I feel like it doesn't apply to every epsilon off of my intuition.
So in general, you cannot compare, you're saying?
I think that too.
Really? Okay, let's spend some time. I know that that is false. So it has to be either that way or the other way around. This is totally ordered, but let me see.
By the containment you have with C epsilon and C, or C epsilon 1 and C epsilon 2, the smallest thing in the set that's contained in the other, if we add something in epsilon 2 that is smaller, the infimum can be smaller. So I want to say that the inequality you have is the right one. Because
So do you disagree with this?
no, I agree with that. I think that causes that.
Okay, so if this is the case, then taking infima over this should be smaller because it's a larger set.
Yeah, at least could be.
Oh, okay.
Yeah.
Okay. Okay, good. Everything is correct now. Okay. So here's the idea, right? If epsilon 1, sorry about this, if epsilon 1 is less than epsilon 2, then C bullets with diameter bound epsilon 1 is also going to be a C bullet with diameter bounded by epsilon 2. In other words, any C bullet that you include in this collection is going to be included here. But then for any element here, you have a number in the reals. So ultimately, you have two subsets of the real line such that one is inside the other one. If you have a larger set, its minimum can be smaller. Because we're taking the minimum, that means that this is possibly smaller than this. Okay, so it is correct. Which means that if I were to take epsilon to 0, this h to the s sub epsilon of a is going to keep increasing quite possibly, but it's going to converge somewhere, possibly to infinity. So limit as epsilon goes to 0 of h s epsilon of a, which is also, based on this, the sup of epsilons this exists. Okay, this limit exists. So this does make sense, okay, for any a and for any s. And this is what is called the s-dimensional outer, or maybe let's not use the word dimension, s-Hausdorff outer measure. Okay, so I'm going to leave that as an exercise, of course. Because for each s, h to the s is an outer measure, you can apply this Cartesian construction to obtain an actual measure if you want. But let's not worry about that so far. Let's just put this. For any s, this is an outer measure recall that for any outer measure, we had this notion of measurability relative to that outer measure. So here's the next exercise. I want to say the following. If I were to take any Borel measurable subset of X, the metric space, recall that Borel measurable means it's a set in the sigma algebra, smallest sigma algebra that contains all open subsets. So for curly B of X, which is the Borel sigma algebra, of X, the Borel sigma algebra is included in any collection of measurable subsets relative to any S. So okay. Now, I'm not saying that for some S, this is exactly the Borel sigma algebra. And in fact, figuring out what is the sigma algebra of S measurable subsets is not an easy question to answer. But for instance, if you were to plug in S equals 0, here's an exercise. So 0 of A is the number of elements in A if A is finite, otherwise it's infinity. So this is what is called the counting measure. And indeed, the sigma algebra of H to the 0 measurable subsets of X turns out to be the same thing as the power set. So that is to say, any subset of X is H to the 0 measurable. That's a nice exercise. And for instance, if I were to take X to be the real line with the standard Euclidean metric, H to the 1 is going to be, well, let's say, it's going to be a constant multiple of Lebesgue measure. And there's a unique number. Let's call it C. Such that for any interval, let's say, for any AB real with A less than B, the one Hausdorff outer measure of the interval will be exactly C times, or maybe let's use a different number, gamma. Gamma times B minus A. It's going to be a constant multiple of Lebesgue measure. And that's a nice exercise. Any questions about these? Okay. Let's look at what happens if I were to use a Hölder function. And for that, to make things slightly more convenient, I want to introduce the Hölder constant, which is like the analog of Lipschitz constant for Hölder functions as well. So let me let a function f from a metric space X to another metric space Y. Be a function between metric spaces and let me let alpha to be a positive number. Then the alpha-Hölder constant of f is the following. So I'm going to denote it by lip sub alpha of f. This is just basic to the Lipschitz constant, but in the denominator I'm going to have distance to the power alpha. And of course, as usual, f is alpha-Hölder. If and only if its alpha-Hölder constant is finite, right? And of course, the one Hölder constant of f is the same thing as the Lipschitz constant. Any questions about this? I should also mention the reason why people sometimes use this notation is that under reasonable conditions, you can think of this expression, so distance to the power alpha, as yet another metric. Now that is not always true in general for arbitrary alpha and for arbitrary metrics. But it is true if you were to restrict, for instance, alpha to be between 0 and 1. So taking a metric and raising it to some power alpha is also called snowflaking, actually. So let X be a set, D be a metric, on X, and alpha be a positive number, then for any alpha less than 1, or less than or equal to 1, d to the alpha is another metric. Is a metric on X. That's 1. And second, D is what is called an ultrametric if and only if for any alpha, D to the alpha is a metric. So for any alpha d to the alpha is a metric if and only if D satisfies what is called a strong triangular inequality. Which says that this distance is not bounded necessarily, it is bounded, but not only is it bounded by the sum if you were to inject another term of the two terms, but in fact it is bounded by the max of the two. It's a nice exercise. So for instance, this d theta metric that we were using on shift spaces is an ultrametric exercise. So this is really something that we were using so far. I didn't mention it when we were using it. Yes?
Are there any, like, when are ultrametrics useful? What do they ensure some properties of metric spaces they have?
Yeah, I mean, let me just say it like this. So ultrametrics show up whenever you have something like a tree structure. So imagine, so here's sort of like a situation where you'd want to perhaps use an ultrametric. Let's say that you have a family reunion. There's a bunch of people that are related, and you want to talk about how close they are. Now, you can talk about how close they are in terms of, where they file their taxes or something. But perhaps because the reunion is in terms of like a family relationship, well, you want to say something along the lines of, oh, who is your, so how many generations do you need to go further to come to have a common ancestor? So that's sort of like, that is modeled by an ultrametric. So if you wanted to talk about the distance between species, or if you wanted to talk about distances between different DNAs, you would use probably something like an ultrametric from an evolutionary point of view. Yeah, yeah. And of course, so the Cantor set in other shift spaces, it's sort of like the most general example of this, right? Because you always have like a bunch of symbols, and you look at the first entry in a ticker tape. Now that tells you in which branch you should be going. You sort of like branch out like this. Yeah, so maybe I should draw that. So for instance, another way of thinking about this Cantor set, so let me just write it like this, is this, right? So you have this binary tree. And you keep going like this. And the C is really sort of like the limit set here. Okay, and of course, if you were to look at, I don't know, like if you were to think of this as a shift space, the first entry, or let's look at it like this. So if you were to take an x, a point, either it is less than 1/2 or it is greater than 1/2. So that's the left-right separation. And to specify a point in the Cantor set, you need to choose this left-right business infinitely many times. And the moment you choose this sequence of lefts and rights, that gives you a unique point. So more formally speaking, this Cantor set is sort of like the, what is it called? The end space of this binary tree. And this is also why, even from a combinatorial point of view, this Cantor set turns out to be very useful. So people, for instance, look at automorphisms of trees like this. Imagine sort of like functions that sort of like shuffle sort of certain branches. There's something called the Thompson group, for instance, that is related to this. These are like a very combinatorial object that shows up in pretty much everything. Okay, any other questions? So, okay, what were we doing? So the Lipschitz constant, Hölder constant. Okay. So I want to do something like this. I want to say if I have a Hölder function and if I have a subset A in X, I want to relate the S outer measure of A to the S prime outer measure of its image. So let me delete all this. Okay, so now I have an alpha Hölder function f. Let me also let a subset A in X and S to be a non-negative number. I want to relate, let me see, I think it is this. Then the S outer measure of the image is bounded from above by this. Alpha-Lipschitz, alpha-Hölder constant of f to the power s times the S alpha outer measure of A. So that's now a proposition. That's a lemma. I think that is correct, yeah.
The exponent S times alpha.
Yeah. So this is the S alpha outer measure. Okay, proof. Okay, so I'm going to use the epsilon versions of this. If I were to take an epsilon, and if I were to take a sequence of subsets of the domain that covers A, whose diameters are bounded by epsilon, I'm going to try to do something with that. Well, if I were to apply f to each term of the sequence, of course, I'm going to get a cover of the image. So D bullet let me define dn to be the image of Cn under F. Then the union of dn's cover the image that I'm going to leave as an exercise. Let's try to bound. Let's try to find the upper bound for this. So I need to look at this, right? Well, the diameter of dn is the same thing as diameter of f applied to Cn. But note that this is bounded from above by lip sub alpha of f times diameter of Cn, because of the alpha property. Of course, to the power alpha. This is constant in n, which means that I can take this out to sup, and then taking alpha power of a bunch of numbers is an increasing thing, which means that I can take the alpha outside the sup as well, which means this is, and it is continuous. Lip alpha of f times sup sub n of diam of Cn to the power alpha, which means that this is bounded by lip sub alpha of f times epsilon to the alpha, because this was bounded by epsilon. Okay? Any questions so far? So I was able to get an upper bound on the diameter of the terms in this image sequence. Okay. Oh, before I erase, here's a quick poll. Which one do you prefer more, the tiny chalk or the large chalk? Okay. But it seems like this is louder. Is this true? Okay, still you like?
I haven't noticed a difference.
Okay, good. Let's continue with the large one then. I just bought these. If you ever watch an OpenCourseWare video from MIT, they have like these like chalks that are basically this size. Like this. Okay. So now what do I need to do? I need to take the power of these guys to the s, right? Because recall that in the statement I had the s power, so the s outer measure of the image. So I'm trying to bound that from above. Maybe I should write it like this. I'm going to write the same thing, but I have some more space over there. This must be an upper bound for the s outer measure with epsilon, that bound that I got, which is this. Lip sub alpha of f times epsilon to the alpha. This is my new epsilon for this. So this is like so. Okay, this is bounded by this. But then this, by the same reasoning, is bounded by lip sub alpha of f to the power s, sum n diameter Cn s alpha. Any questions about this? Right, because this thing inside, diam of dn, is bounded by lip sub alpha of f times diam of Cn to the power alpha. Which means that if I were to pull out this constant, I'm going to get a factor of s. That's why I have this factor, this power s. And then I already had a power s here, which means that I'm going to have s times alpha. Okay? But then if I were to optimize over C bullets, this guy is going to give me h to the s alpha sub epsilon. taking epsilon to 0, I'm going to get here the S alpha outer measure of A, and here I'm going to get the S outer measure of f of A. Which is what I had claimed. Questions? So you see, if you have an alpha-Hausdorff function, you have some bounds in terms of the S outer measures. Okay, so this is going to be important. In particular, if you had a Lipschitz function f, then you wouldn't have this factor, for instance. You would have a nice upper bound. But if you had alpha-Hausdorff, you still have an upper bound. You have an error, multiplicative error, but still. So now, let's look at this phase transition that I was talking about. So far, I didn't do anything with changing S. But to get the Hausdorff dimension, we're going to vary S, the parameter. So now let's look at this. I want to relate the S1 outer measure to S2 outer measure. Okay? So if I had, again, a sequence whose terms have diameters bounded by epsilon and whose union covers some subset A, then by definition, this epsilon version of outer measure would be bounded by this diameter, sorry, S1. Diam C sub n. I want to do S2 actually. I want to take the larger one, S2. Okay, now if I were to replace S2 by S1, here's what happens. You see, I'm going to factor out diam of Cn to S1 times, well, whatever is remaining, right? Diam of Cn to the S2 minus S1, which is a non-negative number because I take S2 to be larger. Let me write it here. Like this. But I chose these terms so that this diam is bounded by epsilon, which means that if I were to take this, I have an upper bound for this. Epsilon times S2 minus S1, sum of diam, which means that if I were to optimize over the sequence, I would get this. So this is S1. You see, this number, the power of this epsilon factor is a positive number. Okay. So I have this. Now what do I need to do? So I want to take epsilon to 0 to get the outer measures, right? But now I have this issue. Either maybe this is positive or infinity or something like that, right? So I need to worry about that. So I have two cases. Case 1 is that the S1 outer measure of A is a finite number. If that is the case, then if I were to take epsilon to 0 in this expression, this is a bounded number, this goes to 0, that means that this is 0. So if S1 outer measure of A, maybe let's write it like this. Two cases. Either the S1 outer measure of A is a finite number, recall that S1 was a smaller parameter, or it is infinity. If this is the case, in this expression, if I were to take epsilon to 0, this guy is going to converge to the S1 outer measure of A, which is a finite number by assumption. This is going to go to 0, which means that if I were to take epsilon to 0, this is going to be 0 also. If the S1 outer measure of A is infinity, well, if I were to take epsilon to 0, this is going to go to 0, but I cannot really conclude anything about S2, right? Because maybe this converges faster, so this goes to 0 faster than this does, this goes to infinity, or maybe other way around or something like that. So this can't say anything. Exactly. But still, this is good enough. Because you see, this is what this says is the following. Look at the graph of the S outer measure of A, where the input is S. I fix A, right? I fix a subset. And I look at the value that this number gives me, or the value of this expression. What this says is that if at some point, okay, it turns out that you're not infinity, then at any time after that, so maybe I should use this, you have to be 0, okay? So if I'm imagining, when I'm graphing h to the s of A as a function of s, if at some point it is not infinity, then after it, it has to be 0. Any questions about this? This is like the fundamental idea behind the Hausdorff dimension. This is my phase transition, if you want. Now note that at this point, I'm not saying anything about the value of this expression at this specific time, at this specific S1 value. Maybe it is finite. I know that it is not infinite, but it is it could be finite, positive number. It could be 0, okay? It cannot be infinity is what I'm saying. And likewise, if I were to invert this idea, if the S2 outer measure of A is infinity, well, as I take epsilon to 0, I know that whatever this is, it's bounded from below by infinity. Which means that if the S2 outer measure is infinity, so is S1 outer measure. Which means that if, for instance, at this value I had infinity, everything before it would be infinity as well. Okay? And in fact, this is the graph. So this is the graph of S goes to the S outer measure of A. This specific value of S, where you have this phase transition, is called the Hausdorff dimension of A. So I can erase this. Okay. Where the phase transition happens, is, by definition, the Hausdorff dimension of A. Is, by definition, and this I'm going to denote by dim sub h of A. And based on this idea, based on this graph that we talked about, I can think of it as the inf, right? The inf of all those s's for which the S outer measure of A is 0. Or equivalently, I can think of it as the soup of all those s's for which the S outer measure is infinity. Okay. Now, on purpose, I'm not saying min here or max here. If I were to look at the S outer measure of A for S equals to the dimension, that measure could be 0, it could be a finite number, it could be infinity. Or infinity. So you know for which parameter, well, once you do the calculation and stuff like that, you know for which parameter the phase transition happens, but you don't know exactly, so this is not exactly the graph, is what I'm trying to say, because I, on purpose, didn't say what the value of it is at this specific value. So let's finish this. So this value, this piece, is exactly the S equals dimension of A. The value could be here, it could be here, it could be here. Okay? So this dimension really, again is giving you the correct sort of dimension notion, but it's not telling you what the size is. Size is about the measure. So to figure out the size of a set, well, you need to compute the outer measure. Okay, so these two calculations, the dimension of a set and the outer measure of a set, these are related calculations, but they are not the same things. Okay. Any questions about any of this? Okay, let's take a 5-minute break, and then when we get back, we're going to continue. Let's continue. So we defined the Hausdorff dimension of a subset of a metric space. Recall that for Minkowski upper and lower dimensions, we had that the dimension of the image of a subset is bounded by the upper or lower dimension of the subset divided by the alpha-Lipschitz constant, or the alpha-Hölder constant of f. The same bound holds for Hausdorff dimension. That's an exercise. That's a nice exercise. That's one. Which means that if you were to have a bi-Lipschitz homeomorphism, the Hausdorff dimension would be invariant. So, exercise. Is invariant under bi-Lipschitz homeomorphisms. Oh, that is not true. What am I saying? I want the Lipschitz constant to be 1 under, hang on a minute, bi-Lipschitz. I think this is true still, under bi-Lipschitz homeomorphisms.
Were you looking for like isometry or something?
Certainly it is invariant under isometries. Yeah, because if it were an isometry, this would be 1 for alpha equals 1. Let me think. Oh, that's because this is not Lipschitz constant, it is alpha itself. Alpha, this was the correct expression, divided by alpha. Okay, now it makes sense. Okay, that's what I'm trying to say. If f is a function whose alpha-Hölder constant is finite, that is to say, if it's alpha-Hölder, then you have this bound. Same bound holds for Hausdorff dimension. In particular, Hausdorff dimension is invariant under bi-Lipschitz homeomorphisms. For bi-Lipschitz homeomorphisms, alpha can be taken as 1, right? This makes sense now. Another exercise is that we had talked about how Lebesgue covering dimension of a subset is bounded from above by the lower Minkowski dimension, which syntactically is bounded from above itself by upper Minkowski dimension. The exercise is that the Hausdorff dimension of a subset is in between the Lebesgue covering dimension and the lower Minkowski dimension. So you have, we discussed so far, that means 4 different senses of dimension at the very least. Okay? So sometimes these values are the same, sometimes they aren't. Okay? So now let's tie this back to iterated function systems and the dimensions of attractors. Recall that the Moran-Hutchinson formula was about that. So exercise. Based on these bounds, we already have, in fact, upper bounds for the dimensions of the attractors of iterated function systems. So let S be a B-IFS with unique attractor A sub W and coding map. Phi sub W, it's from the shift space with n symbols onto the attractor. Recall that in the context of Hutchinson coding theorem, we show that this is onto, and it's alpha-Hausdorff. For alpha, I didn't compute when we were doing the proof, but it's computable. So is alpha-Hausdorff the dimension, the Minkowski dimension of this shift space we discussed, and the part of the exercise is to compute the Hausdorff dimension. So, well, the Lebesgue dimension is 0. Hausdorff dimension I want you to compute. So this is alpha-Hausdorff. So find the value of alpha. Find a nice value, best value. So the largest value of alpha. Find a large enough value of alpha. That's part 1. Part 2, compute that the Lebesgue dimension is 0. This was part of a previous exercise, I think. Minkowski dimension relative to these, one of these d theta metrics is log n divided by log theta. Let me also mention that this value of alpha 2 is going to depend on, in fact, theta. Because d theta is the metric that I'm using after all. Compute that this is also the Hausdorff dimension. Relative to the d theta metric. Well, if this attractor is the image of the shift space under this map, if you know the dimension of this, and if you know the alpha-Hausdorff or the alpha constant of this guy, using these, you have upper bounds as to what the dimensions are, as to what the dimensions of this guy is. At this point, you see, we don't know if the Hausdorff dimension or the Minkowski dimensions of the attractor are the same number. It turns out that it is true under mild assumptions, but at the very least, we have that these are these expressions are all bounded by, well, 1 over alpha times this expression. Log n divided by log theta. It's going to turn out that once you compute a nice value for alpha as a function of theta, whatever that expression is, it's going to cancel out this factor of theta, of log theta, and you're going to get something like log of n divided by log of 1 over capital L, let's say, where L is the maximum Lipschitz constant of one of these guys. Okay? So ultimately, this upper bound is not going to depend on theta, which does make sense because theta is, if you don't have the shift space, it has nothing to do with a sub w. It doesn't see what theta is. So ultimately, the upper bound that you get also shouldn't depend on theta from a heuristic point of view. But point is, what we're trying to do now is to come up with explicit expressions. We want to not only get upper bounds, but exact bounds. Okay? So now I think we can start talking about the proof of the Moran-Hutchinson formula. Dimension formula. Of course, at this point, we also have this other number that we can compute significantly easier than any of these, which is the upper similarity dimension of an iterated function system. So let be a B-IFS. Let's assume it's not sort of like this trivial version, which means that let's assume that none of the contractions in W is a constant function. We had talked about what to do in this case. It was an exercise that I left. I'm going to have 3 assumptions. And basically, the current research around these things is sort of generalizing or relaxing one of these 3 assumptions, or maybe multiple. If, first, I want my ambient space X to be a nice space, that is to say, at the very least, it should be Euclidean. It's kind of mysterious how, when you assume that your ambient space is Euclidean, you have these like nice properties that is not necessarily available for general metric spaces. Second, I want each contraction in W to be a similitude. So for each I, Wi is a similitude. That means, or another word for it is a similarity transformation. All it does is it scales, okay? And it can shift, of course, too, but i.e., it's a bijection and for any 2 points in the space, the distance between them, between their images rather, is not only bounded from above by the Lipschitz constant times the distance, but in fact it is equal. And third, I want the open set condition. Let me just remind you what that was. It's a certain separation assumption. I want the images of these contractions to be essentially not overlapping too much. This means that there is a non-empty open subset of X that has the following two properties. Such that my open set is, using dynamics terminology, forward subinvariant under any function in the iterated function system, and the pairwise intersections is empty. So I from 1 to n, j from 1 to n, and not equal to I. So the intersection of the ith image and the jth image of U is empty. These are my three assumptions. Then, right, these are the assumptions. For S equals the upper similarity dimension of W, recall that this was the unique number. So such that Lipschitz constants to the power S equals 1. The S-dimensional or outer s-Hausdorff measure of the attractor is a positive finite number. Okay. Now, the only S for which the outer measure is a finite but positive number, the only number for which this happens, S has to be, so the only number for which this happens is the dimension, right? Because there you have the phase transition. If for this S, this number is a finite number, anything before it, the outer measure has to be infinity. Anything after it, the outer measure has to be 0. Therefore, the Hausdorff dimension is equal to this. And third, the Minkowski dimension of the attractor 2 is the same thing, is the same number. Okay, so this is the Moran-Hutchinson formula. These dimensions, in general, they're not easy to compute necessarily. Often it takes some calculations and stuff. But if you have these niceness assumptions, then dimensions are given by this number that is easier to compute, relatively speaking. So this sum is I from 1 to n. let me add two more items actually that I'm not going to prove, but I just want to mention. In fact, this is also the same thing as what is called the packing dimension. I'm not going to define it, but it's a notion of dimension, it turns out, that is somewhat dual to Hausdorff dimension. Recall that for Minkowski dimension, one of the characterizations was I want sort of like points that are like separated from each other. If I were to use the same thing, and if I were to adapt it to this Hausdorff business, there's what is called a packing outer measure. There's a packing dimension. I'm not going to define all this, but I'm just going to say it is also equal. Some of you have been looking into this packing dimension already. If you want to read more about this, Falconer has a nice description. So this is the packing dimension. And 5, this is what is called the Bowen formula, in fact. And this is sort of the starting point, or one of the entry points, perhaps, of what is called thermodynamic formalism, where you really take these ideas of dimension and, in fact, constructing a notion of dimension that is stable or robust, and applying it to dynamical systems. The upper similarity dimension is, in fact, also the unique zero of what is called the pressure function. So of the pressure function. Of W. Let me write down the pressure function somewhere. Okay, I'm going to write it here. So the pressure function will be pressure function at the value t is the following limit. Limit as n goes to infinity of 1 over n sum over all fixed points. Let me delete this. At this point, we know the upper similarity dimension. All fixed points of sigma to the n. So I want returns at time n of log of the Lipschitz constant of the cocycle that we defined in the definition in the Hutchinson coding theorem to the power t. Okay. So this somehow should remind you of, well, maybe it shouldn't, but it does remind you of the zeta function if you look into it for some time. So recall that in the zeta function, which we defined a long time ago, we were using these sets, the fixed point of the nth iterate, and then we put that into a power set. Well, in the zeta function that we defined, we were just looking at the number of things in that set. Well, instead of having just one here, you have sort of like a density. You're weighing different sets of fixed points of the nth iterates using specific functions coming from the dynamics. And that gives you what is called topological pressure, and that's why this is called pressure function. I'm not going to even go even further as to why any of this makes sense, but I just wanted to, at the very least, mention these two items. Okay, So there are papers by Banerjee, I think. I've put on their resources. Other people have works on this as well. So maybe I should say Bedford, Ruel, Banerjee, and so on. And for this, look at Falconer. So Falconer. That's a statement. Okay? Any questions? So to wrap up, if you have a nice iterated function system, dimensions, pretty much any sort of dimension is given by the upper similarity dimension. Okay, I'm out of time. Next time we're going to start proving this. Thank you. I'll see you on Thursday. Okay, let's start. Good afternoon. So today we're going to start the proof, probably not finished, but we're going to start the proof of the Moran-Hutchinson formula. So we have a couple of things we need to do. So we have a certain candidate as the Hausdorff dimension or whatever dimension of the set that is the attractor of some iterated function system. So the first item, remember, I'm going to remind all of that in a second, but the first item was that the S outer measure of the attractor is a positive finite number. So we're going to do that in two steps. The upper bound and then the lower bound. The upper bound is going to be rather straightforward compared to the lower bound, but still. So we're going to start with upper bound and then go to the lower bound and so on. Okay, here's a correction. I mentioned last time that this upper similarity dimension, this number you can associate to any iterated function system, is also the unique zero of this pressure function you can associate to your iterated function system. When I was defining this, I defined it wrong. I put the log inside the sum. It should be outside the sum. Just wanted to make sure that that is clear. Okay. So Hutchinson dimension formula. So we have n many contractions. Recall that, so let me remind you the assumptions and let's fix some notation as well. Let me let, okay. Capital Phi, the coding map. Recall that this was a Hölder onto function from the shift space to the attractor. Let me let L sub I, the Lipschitz constant of the ith contraction. Just this is so that we have an abbreviation. The max of all Li's I'm going to call capital L, and the min of all Li's, which we're going to have to use for the lower bound, I'm going to call lowercase l. And recall that we're assuming that none of these is a constant function, which means that the lower Lipschitz constant is going to be a positive number. So, that's equal to L, and this is a number strictly less than 1. So these two numbers are going to be important for us. Yeah, this is all I want for now. Let me remind you the assumptions. First assumption is that X is Rd, so it's some Euclidean space. Second assumption, that each of these wi's, not only are they contractions, but in fact they are similitudes. So which means that this distance is exactly L sub I, the Lipschitz constant, times the distance between the 2 points. Which in particular tells you that Wi scales the diameters by this. So maybe I should write it. If I were to start with any subset of X, apply Wi to it and look at the diameter, this would be exactly Li times the diameter of A. Okay. And then the third assumption, of course, is that this iterated function system satisfies this open set condition. So there is an open set, non-empty open set, U, which is a subset of the Euclidean space, such that the image of this U under any of the contractions is inside U. But on the other hand, any two images are disjoint. So for any I, the ith image is inside U. And for any two distinct indices, the ith and jth images are disjoint. Of course, the attractor 2 has this property, but it doesn't necessarily have this property. You should think of, for instance, the Sierpinski gasket is empty set. The point is that even though quite possibly the attractor or the iterated function system doesn't have this total disconnectedness property, at the very least, there's a proxy where you can do that. Okay. Oh, of course, the important thing, let's also fix S to be the upper similarity dimension. So upper similarity dimension of W, by definition, is the unique number, non-negative, such that unique S such that if I were to take the S power or S powers of Li's and add them up, I get 1. So okay. First claim is that the S-dimensional Hausdorff measure is a finite number. So, proof. So first, I want to say that the S-dimensional measure of A sub W is finite. That's my first claim. Note that this immediately shows that it gives you an upper bound for the Hausdorff dimension. Because recall, this is the graph for the S-dimensional Hausdorff measure of A sub W, and the horizontal axis is the S parameter. So somewhere here, we have this S. What this is saying is that if I were to plug in this S parameter, the value, right, is not infinite. Which means that, okay, so it could be 0, right? We're going to need to sort of bound it from below as well. But if we can show this, that would mean that at the very least here I should have observed a phase transition. Which means after that, it's going to be 0. Okay? Now the problem at this stage still will be this, right? Like this graph could be like this perhaps. So maybe the phase transition happens way before. If I can show that, oh, the estimational Hausdorff measure is not this point, it's not 0, but it's finite, it's a positive number, then I'll have the lower bound as well. So it could be like this at this stage, it could be like this, or it could be like this. If you want to show that ultimately that this is the graph. But if we can show this, we would have that the Hausdorff measure, Hausdorff dimension of the attractor is at most S. That's going to give us the upper bound. Any questions about this? Just wanted to make sure that I'm recording. Okay. Okay. Now the idea is the following. So fix n and consider the nth images of the attractor, where I'm choosing my sequence to be a fixed point of the nth iterate. So it's an n-periodic fixed point of the shift. This is a finite set of sets, and certainly each of these sets is a subset, because under any one of these contractions, recall that this is just a composition of a bunch of contractions, A sub w is invariant or subinvariant, which means that each of these is a subset of A sub w. And if I were to take the union of these, I would get everything. So I'm going to leave that as an exercise. So exercise. This is a cover, finite cover. Of A sub w. Now, what is the size of this? So that is to say, if I were to look at the sum of diameter of any one of these sets to the power s, what can I bound it from above? So let's look at this. I'm just going to add all of the diameters. And then I'm going to raise them to the power s, because I'm trying to bound from above the estimational outer measure, or in this case, measure itself. Okay. Now, this kind of looks perhaps weird a little bit, because when we were discussing Hausdorff measures and other things, we always had sort of a sum over integers. But here, the enumeration is different. Okay, it's just a finite. I'm enumerating over a finite set. So this summation makes perfect sense. In a sense, this makes more sense from a dynamical point of view, right? Because this is a dynamically significant set. Okay. Now, what is this? Each function inside lowercase phi is one of these wi's. Well, which means that the composition of them, that is to say this thing, is also a similitude, which means that I can rewrite this diameter as Lipschitz constant of this function times diameter of the attractor. So let me write it here. So I'm going to continue here. This I'm going to have to raise to the power s, right? Because this s is applied to the whole thing. So this to the s times the diameter of a sub w to the power s. So I'm adding all of these, but as you see, this factor doesn't depend on omega, which means that I can think of this as really this. Okay, now what is this? Well, this is nothing but the product of Lipschitz constants of the contractions that make this up. So this is L sub W0 times L sub W1 dot 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 L sub W n minus 1 to the power s times diameter of a sub W to the s. This, of course, is a finite number because a sub w is a compact non-empty subset. Its diameter is finite. That diameter to the power s2 is finite. So this is not an issue. Okay. Now, when you think about this, if omega is varying over all n periodic points of the shift, and if I'm taking every single such omega, this I can write it like this. So taking sum over the n periodic points of shift is the same thing as taking these n summations, iterated sums. And of course, I can distribute this power to each of these factors as well. So these are my summands, and I have an iterated sum. But note that, for instance, all the factors here, except the last one, I can take out of this summation because they are constant in omega sub n minus 1, and so on. Which means that I can write this like this. Can factor out this summation. And then, of course, I have the diameter. But once you do this factorization, it doesn't matter what you call this index. It's a dummy variable, after all. This is just this sum to the power, how many I have, lowercase n. So let me just write it like this. This is nothing but I from 1 to n, L sub I to the power s, raised to the power n. I have n copies, lowercase n copies, times its diameter. But we chose s to be the upper similarity dimension. which means that each of these we chose to be 1. Okay, so I have 1 to the power lowercase n times diameter. Okay, this is equal to diameter of a sub w to the power s. In other words, this summation equals to the diameter of the attractor to the power s. In particular, it's a finite number. Any questions about this? Okay. Now, for any lowercase n, I can do this. So now, I want to bound the estimational Hausdorff measure. So I need to fix an epsilon, and then I'm going to optimize that, right? So for each n, I'm going to consider one of these covers. Fix an epsilon. Now the diameter of this for any fixed point of sigma to the n is bounded by, well, by the same sort of reasoning here. I'm going to have lowercase n copies of some Lipschitz constants. These are all bounded by capital N, right? That was the maximum of all of these Lipschitz constants, which means that this is bounded by uppercase n, uppercase L to the power n times diameter of a sub w, which means that if I were to, I can always take lowercase n to be large enough so that this value is less than epsilon. Such that for any omega, which is a fixed point of sigma to the n, the diameter of each of the elements in this cell, or in this cover, is bounded by epsilon. Uppercase L is less than 1. Okay, so I can do this. Which means that if I use this lowercase n in this cover, this sum should be an upper bound for the epsilon version of S outer measure. So this n depends on epsilon, of course. Then this guy is bounded by this. I am of this set to the power s. Which I just showed is equal to this guy. So this sum is equal to this. For any epsilon, then I have an upper bound as to what this value can be. Well, the estimational outer measure is nothing but as this, the limit of this as epsilon goes to 0, which can only increase, but I'm saying that the upper bound is this, which means that, if I were to take the limit too is going to be bounded by this. By squeeze theorem or whatever. Okay. Am I losing you? questions, comments?
I think like the overarching idea makes sense. I got a little bit lost on the right board.
Uh-huh.
All this, I'm
I think I was going to ask a little bit for some more elaboration on how you got it into this sort of factored form of raised to the like lowercase n down here. That part blew over me.
So this from here to there?
From there to what's right beneath it.
From here to there?
Yes.
Oh, well that's because, okay, so would you agree that omega 0 here is a dummy variable?
Mm-hmm.
Okay, so I can I can use any letter I want. And I can in fact use the same index for each of these sums because they're all dummy variables. It's the same number, whatever this is. Like the value of this doesn't depend on what omega 0 is.
Okay, I sort of.
Which means that this sum is the same sum as this sum.
Okay, I think that makes a bit of sense.
Yeah.
A little hazy, but like I think I might think about that.
Yes. Yeah. I mean, so if you read this proof in Falconer's book, he doesn't really use this notation. But because I'm a dynamicist, it makes more sense for me to write it like this because, this sort of like suggests different ways of generalizing this idea. If you had the subshift, for instance, instead of the full shift, a similar argument would suggest certain things. I should also mention, for instance, in this proof, we actually didn't use any of the assumptions, any of the extra assumptions. What would have happened if we had an arbitrary B-IFS is that this would be this. So the upper bound still works, actually. The lower bound doesn't. Okay? So the upper bound you have for an arbitrary B-IFS. Okay, so that's that. Now for the lower bound, we're going to have to develop some technology. Okay, so that's that. It's a positive number. That's what I want. Right? Because so far, we know that if this is this specific value s given by the upper similarity dimension, we know that at this stage, after it, it has to be 0. The problem is that maybe this phase transition happens before. So in order to avoid this, we want to say something like, oh, the s-dimensional outer measure, or measure itself, is a finite number. When you have that the s-dimensional measure is finite here, which means that before it, so it means that the phase transition happened exactly here. Then we would be able to complete the graph. Okay, that's the point. Okay. So we need two pieces of technology, let's say. One of them is what is called the mass distribution principle. And the other one is a certain covering lemma. Need I mean, maybe you don't need it, but the proof I'm going to present does need it. And second is a covering lemma. Let's first discuss this mass distribution principle. It's a very straightforward idea. It says the following. Well, instead of trying to lower bound the s-dimensional Hausdorff measure, which is sort of like a geometrically significant sense of size, well, try to bound it from below, or instead of bounding the size of this a sub w relative to this geometrically significant measure, bound the size of a sub w relative to some other measure. Okay? If you can bound that, then we have this inequality. So let me be more precise now. This is a rather general statement, and this is one of the sort of methods of bounding from below the Hausdorff measure of whatever. So let me write it in general. Let X be a set, D be a metric, and mu be a measure. On X. Okay. Let me also let S a parameter and a subset. If, that's the first part, okay. If there's a number, gamma, and an epsilon star, again a number, such that for any subset of this guy, you have that if the diameter of B is bounded by epsilon star, then the S outer measure of B is dominated, the mu measure of B is dominated from above by the S outer measure. Times is constant, of course. That is to say, for small subsets, this measure gives less value, less size, up to some multiplicative error compared to the s-Hausdorff measure. And if second, if the measure, in fact, of this subset turns out to be positive, then Hausdorff dimension of B is bounded by epsilon, by S. Okay. Now, part of the proof of this lower bound is going to be the construction of this mu. Okay? And this construction of this mu is going to come from dynamics, basically. It's going to be this dynamically significant measure. Okay. Let's try to prove this.
Can I ask a question?
Yes.
About the general strategy of the proof here. It seems like we're looking at the S value that we've already determined is like the phase change.
Yes.
Location, and we're proving that it's not part of like the previous infinity phase, I guess,
Yes.
or the 0 one.
Yes.
Have we done anything to prove that every S less than that is infinity and every S greater than that is 0?
Yeah, I mean, I mentioned that last time, but it comes from this. Remember last time we were talking about what happens if you were to change the S value. We had this inequality. From that, it follows.
Okay. So we already proved it before?
Yes, yes.
And then I guess why is there a problem if it's infinity or 0? Like, doesn't the phase still change?
Well, I mean, so far, if we didn't have this, I said that this is our specific S value. We know that so far that it is not infinity, which means that after it, it must be 0. But maybe the phase transition happened before. Maybe this is what happened.
Okay, I see.
So we have an upper bound as to the parameter for which you have the phase transition happens, but maybe it happened before. But of course, if you don't have, that's the point, if you don't have 0 value here, which could have happened, if you don't have 0 value here, but if it's not infinite, which means that it has to be finite, which means that the phase transition had to happen exactly at that value. Yeah. Okay. I'm confused. I feel like the item one doesn't make sense. Oh, of course this should be, I think, A. Okay. I'm trying to say something about A. Okay, so the statement is that if for the subset A, any subset, any small enough subset of it has, oh man, this still doesn't make sense. Does any of you sort of know how I should change this? Let me think. Okay, ultimately, I want this, okay? Let's try to reverse engineer this statement. So somehow I want something like this, such that this works. Okay, let's try to think. Let's try to first write the proof, and then based on the proof, we can figure out what we proved, what we need to prove. So, proof. So need ultimately, this is what I want, which means that if this is S, in order for the dimension to be bounded from below by this, well, it must be the case that the phase transition happens later, right? So because this Hausdorff dimension you can think of as infimum of all those sigmas, maybe t's, let's say, such that the t-dimensional outer measure is 0, and also the sup of all those t's such that the outer measure is infinity. Okay. Let's recall this definition as well. Right? C is a collection of countably many subsets whose diameters are bounded by epsilon. Okay, let's try this then. I'm going to rewrite it once we figure out what needs to be proved. And of course, I can take in this expression epsilon to be less than epsilon star. After all, ultimately, I'm going to take epsilon to 0. Say epsilon is not larger than epsilon star. Let me take a cover. By subsets whose diameters are bounded by epsilon. Okay. So I need to look at this expression. Diameter of Cn to the power s Yeah, maybe the statement is something like, if there are these things such that for any b, for this happens, and A has positive measure, then the dimension is positive. Maybe something like this. Okay. So ultimately, I need to bound this from below by mu. Maybe instead of here the S outer measure, I have the diameter. Oh, maybe the statement is this actually. Let's see. Yeah, sorry for this.
On a slide that I'm looking at, it looks like it is the whole, well, they have a metric space, but the whole space is the thing that they have inside. So it looks like it would be A for you. Mu of A is associated with gamma diameter A. Yes, because suppose E is a metric space, and then it has E's. If you want to look at this,
Yeah, yeah.
spark you.
Just. Okay, so I did correct it. It was diameter. You see, I was in the right track. This is the statement. So hang on, let me just finish it. If no, I don't want to mess up everything. So such that, okay, diameter, okay, okay. Okay, the statement I wrote was the following. Here, from here I messed up. So if this is that, if, okay, such that, anyway, I think this is correct. Because if I have this assumption, right, because each Cn has diameter bounded by epsilon star, I know that these guys, I can apply this expression to it. So, hang on, getting confused again. Can I have a look again? Sorry. Yeah, just put it here. E constants. Okay, let's continue. I mean, this seems something like this seems to be correct, but I can't right now see how to prove this actually. But ultimately, something like this should be the case. Okay, I have it. Okay, good. Okay. Ultimately, I want this. Okay, the point of mass distribution principle is to be able to bound the Hausdorff dimension of a subset. Now, I fix, and somehow, let's say that this first item is true. And I'm taking epsilon small enough, lesser than this epsilon star given by the assumption, and I take a cover. I count up the many subsets, such that each of the subsets in this cover that I choose has diameter less than epsilon. And of course, it has to be a cover. Now, by subadditivity, or monotonicity of measures, well, this is a smaller set than this, which means that the measure of this guy is larger. But then if I were to put the measure inside, I don't know anything about whether or not these are disjoint, but ultimately, this cannot decrease. Okay, now I have it. Okay, now, assuming this, because any Cn can be chosen as a B here, right? Each of these expressions are bounded by this. And I can pull out the gamma, of course, because it's a constant in n, so that I have this. Okay? So mu of A, the measure of A, relative to this measure that you somehow find, is bounded by any expression like this. But if I were to optimize over the sequence, over the cover C, meaning if I were to take infima over C bullets, well, this is going to give me the s-dimensional outer measure of size epsilon. So gamma times okay. Yeah, sorry, I just it took me some time. Let me just rewrite it here. But of course, if I were to take epsilon to 0, so to get here the s-dimensional outer measure, this expression can only increase. Okay, so that I have mu of A is dominated by gamma times the s outer measure of A. Well, if this is the case, and furthermore, if mu of A is positive, and this is a positive number, that means that the s outer measure is also positive, which means that this is true. Okay. Right, because if I have this bound, and if, in addition, mu of A is positive, well, if this is bounded by 0, this too is bounded by 0. Okay, again, drawing the phase transition. I'm saying that if I were to look at the value s, the s-dimensional Hausdorff measure is not 0. Okay? Well, the graph could be like this. Maybe the phase transition happened later, but it cannot happen before. Okay? That's why, so maybe it happened here, or maybe it happened here. But in any event, you're bounding the dimension from below. Okay? That's the idea. So, apologies for this. Let me just restate the mass distribution principle. Now I have it. Okay, sometimes it's good to just prove something and then look at what you actually proved. A lot of theorems are actually proved this way. You try to prove something and then you cannot prove it, and then you prove sort of like a version of it, and that becomes a theorem. And ultimately, this is why in a lot of like PDE papers and stuff, you have all these like bizarre assumptions, because you cannot prove it otherwise. You assume what you can prove, what you can use. So mass distribution principle. Let X be a set. D be a metric, and mu be a measure on X. Oh, I'm also choosing a number S and a subset in X. I want to bound the Hausdorff measure of A from below. If there's a number gamma and there's an epsilon star positive, such that for any subset of, instead of A, let's use X, because that's what we ended up proving. If the diameter of B is bounded by epsilon star, then mu of B is bounded from above by gamma times diameter of B to the power S. If this happens, this is a hypothesis, then so item 1 in the mass distribution principle is that if you have this, then this. Item 2, if in addition, oh, this should be A, sorry. If in addition, mu of A is positive, then the Hausdorff dimension is bounded from below. That's a statement. That's what we proved, actually. Apologies for this. Oh. Any questions? OK, let's take a break. When we come back, we're going to talk a little bit about some of the things. Item. OK, let's continue. Apologize for this blunder. Every semester one has to do something like this at least once. And this was this semester's. OK, so we have this mass distribution principle. So ultimately we're going to need to use this to bound from below the Hausdorff measure of the attractor. That's what we're going to use. Here we know everything, right? So we know everything except the measure, of course. X is the Euclidean space. D is the Euclidean distance. Okay, we know the value of S we should be using as well. We know what subset A we should be using. We don't know the measure. We don't know the measure that we should be using. And part of the proof is to come up with this measure. So that's the first item. Second item is going to be this covering lemma. Let me write that as well. Oh, by the way, I've put this choice of the subset over here. So the statement is like if you have a set X with a metric D and a measure mu, and if you chose a parameter S, then if you have this expression for some gamma and for some epsilon star for any subset B of X, if the diameter of the subset B is bounded from above by epsilon star, then you have this bound, this relationship between mu and the diameter. Then for any mu measurable subset, the measure of that subset is bounded from above by the s-dimensional outer measure up to this constant, multiplicative constant. And in addition, if mu of A is positive for some A, then the dimension of that A is bounded from below by S. That's probably a better statement. Now this really comes from fractal geometry, where the emphasis is on understanding the Hausdorff measure, because that's sort of like what you do. Because from a geometric point of view, the Hausdorff measure is more significant. But if you're approaching this from a dynamical point of view, or from a more general measure theoretical point of view, what is important is mu, being able to construct the mu. Okay, so the covering lemma. Let X be a set, D be a metric, and mu be a measure. On X. Let curly U be a collection of open subsets of X. That are pairwise disjoint. So I have a bunch of blobs. The covering lemma, it could be finite, it could be infinite, whatever. The covering lemma is about taking a ball and looking at the maximum number of cells in this collection that you're going to be able to hit using that ball. So for instance, in this configuration, if I were to choose a small enough ball, I'll be able to hit exactly one cover, one element. But maybe if this is like very close to each other, okay, so maybe the upper bound is 2. Okay, so let me be more specific. What I need is, well, first of all, I need a control. I need some sort of control over each of these, the sizes of each of these cells. And I need some relationship between mu and d. Okay? If there are two numbers, lambda and rho, such that for any r positive, oh, it should be the other way around. If there are lambda and rho, and for any u in curly U, there are 2 points, x lambda, that depends on u, and x rho, such that I'm going to fix an r before. Okay, fix an r. If there are lambda and rho, such that for any u in U, there are 2 points. Oh man, I'm messing up the quantifiers today. If there are 2 points such that the open ball centered at x sub lambda is inside U, which in turn is inside the open ball centered at the other point of radius rho times r. Okay. Then for any x and x, the number of u's in U such that the ball of radius R centered at X intersects U closure is non-empty, is bounded from above by 1 plus 2 rho divided by lambda to the power, let's say, d. I didn't say anything about mu yet because I forgot. Let's say this. Such that there's a gamma positive, blah, 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 times this. Okay. I think now it works. So mu is supposed to be something like a volume. I'm saying that d is a number such that balls have mu size that grow like r to the d up to some constant gamma. Okay, so the covering lemma is, let X be a set, D be a metric, and mu be a measure on X. Let U be a collection of open subsets that are pairwise disjoint. Let R be a positive number. If mu is so that there's a gamma such that for any ball of radius r, the mu size, mu measure of the ball, open ball, is gamma times r to the d for some fixed d, of course. Not the same d as the metric. And if there are two numbers, lambda and rho, such that for any open set in my collection, there are 2 points in X, such that U contains the open ball of this size, of this radius, lambda times rho, and U itself is contained in an open ball of this other radius, then for any open subset of radius r, the number of U's in my collection that hit this open subset is bounded by this specific number. Okay. So this is sort of the idea. This is one of the U's. And maybe let's do something like this. Maybe it's like this. You see the different elements in curly U, they need not be of the same size, but I want something like this at the very least. There is like one ball I can fit in, and there's an upper bound, upper ball, something like this. So this is x lambda u of radius lambda times r, and this is x rho u of radius rho times r. I want to be able to do this for any subset u in curly U. Then I'm saying that this is bounded. And of course, we're going to apply it to the case when X is Euclidean space, D is the standard metric, and mu is volume. The same idea works. Okay. So maybe I should I feel like I'm pushing your patience today. So let me just say it in words. I'm going to write it using a different color. If U is a collection of disjoint open subsets, such that any U in U contains some ball of radius lambda rho and is contained in turn by is contained inside some other ball of radius rho times r. A ball radius lambda r and is contained in a ball of radius rho r, in a ball of radius rho r, then any ball of radius r hits at most that many u's. Radius r it's at most 1 plus 2 rho divided by lambda to the d, where d is the dimension of the space. Maybe I should write it like this then. Disjoint open subsets in are M, and this is M. Okay. So this is sort of like the bound I want. I have 5 minutes. Questions? Compared to how hard it is to state, it's actually not that hard to prove. Yeah. So say I have a ball say I'm choosing one of these open subsets in my collection, and I have a ball of size of radius r that hits one of these the open set that I chose. Then we have the following. So let me let z to be in the intersection. So I claim that, in fact, U is contained in the ball with the same center as this ball that I'm using of radius 1 plus 2 rho times r. So if I were to take a y in U, in fact, I can use the closure, I believe. Well, U is inside. This ball, which means that its closure has to be inside the closure of this ball. The closure of the open ball is a subset of the closed ball. Oh, but then I can bound the distance between y, the point that I chose, and the center using the triangular inequality with this term in the with this point in the intersection injected. Okay. Oh, maybe I want to use this point actually. Today was not a good class. So this is bounded by R. Oh, okay, that's fine. So this is bounded by the diameter, right? Because both of these points, nice, both of these points are inside U prime, or U bar. Well, that's a subset of this, which means that these 2 points, so the distance between these 2 points is bounded by the diameter of this set, which is bounded by twice this. So that this is bounded by 1 plus 2r, 2 rho times r. That's what we have. Okay. So we have the claim. Do I have time? I don't have time. The next thing, so the next step in the proof is to say that, oh, each of these U's contain some ball of radius lambda r. Well, I know that that ball, each of such balls, has to be of size lambda times rho r to the d. Well, that should be, the sum of them should be bounded by the sum of these guys. And that's what that's how we get the upper bound, this bound. I'm going to do this next week. I apologize for today. I was all messy, but yeah. Anyway, thank you. I'll see you next week.